Hello everyone, I'm Amin, and today we're going to talk about this paper called NeRF, the representation seen as neural radiance field for view synthesis. This paper has been published in 2020 in ECCZV, and before any further ado, let's hop into it. So, the first question is, what exactly is view synthesis? View synthesis is a task of combining a number of images that, for example, we have from a specific Lego truck or a Lego bulldozer, and by combining those images together and passing it through a specific view synthesis model, which I'm going to discuss about in a few more minutes. By passing it through the model, we are going to be able to generate a 3D representation of that object. And this object could be described in many different forms. One of the forms is for every specific point in 3D. By knowing the X, Y, and Z, we are going to be able to know the color of that part and also the density. And as you could see here, this is the result of this paper that I'm going to talk about. And as you can see, it's done a pretty good job. Another thing that we need to know about the view synthesis model is that they come in two different ways. One of them is neural networks, which we are already familiar with. The way that neural networks work is that by using a deep convolutional, or not just convolutional, any kind of network, by passing the and of course, we need a lot of data for deep neural networks, and that's one of the downside of it because deep learning is basically on computational power and a lot of data. And by using that deep neural network, we're gonna be able to generate a 3D representation over that object. The good side is that we are going to be able to generate a 3D representation pretty fast from a bunch of images. But one of the downside is that we need a lot of data for these, and it might not be very accurate compared to other method that we're going to talk about. And the other method is the computer graphic method. The way that they don't use any machine learning techniques in order to generate a 3D representation. In fact, they use traditional and old computer graphic methods by combining and knowing the exact location of the two cameras that got the images from, and by knowing their each feature point from every pixel and frame, and by combining them they are eventually going to be able to estimate a good 3D representation of that object. And here is another example of the results that these guys have got from their representation and their paper. And far from the previous page that I showed the Lego truck, we could see that their method works pretty well with different objects such as chairs, still the logo block, these circle thingies which I'm not familiar with and I don't exactly know what they are, also the drum, the microphone, the hot dog, the ship, and the plant. And so it's a very good to generalize over different datas. And the very important thing about it is that in their approach, they needed a lot of data to generating these things, and they are basically trying to train a neural network. They are overfitting these data on the network in order to memorize and come up with a very good 3D representation of those data. And I'm going to go into the details of this method. Okay, next up, we need to know exactly what kind of features we're going to work with in this project. And also we need to know the notations. First of all is the X vector, which consists of three features called X, Y, and D. Each one of them shows the position of that point in the 3D coordinate system, which is pretty obvious. Other than that, it's vector D, which shows the direction of the way that we're looking towards that point, which is shown in the paper with two parameters, theta and phi. However, in their code and their way that they implemented the model, they represented the entire thing, the direction vector, as a 3D vector, which whatever vector you have in the space has a specific x hat, y hat, and z hat. And by using those three numbers, they are able to determine the direction of vector D. Other than that, we have the color vector, which shows for a specific point, for a specific x, y, and z, and the direction D, there is going to be a specific color, which could be easily represented as a 3D vector with R, G, and B, which is basically red, green, and blue. And another feature is the parameter sigma, which shows the density of that specific point. An important thing that we need to consider is that we could easily select a point in the 3D space which is thin air or a complete void. So the color does not have any specific value if you look at in that case. So this value is going to be something very small if we were looking at the thin air, because it has no density and nothing in that space. And those are the features that we need to know in order to go on with this presentation. Okay, next off, I'm going to go into the details about the entire systems model. First of all is a neural network that we're going to use, and we pass a 5D input in it, which 3D of that input belongs to X, Y, and Z, and 2D of it belongs to theta and phi. And by going through that network, we are going to have a different outputs, such as the density, which is only related to the parameter x, y, and z. However, the output parameters RGB from the color vector are dependent to both the position x, y, and z, and also the direction. And by knowing those outputs from the previous network, we are going to go in a volume rendering space, which is a graph that shows for every location in the space there is going to be a specific density, and by knowing those density throughout the space, we are able to estimate the color. How are they going to estimate the color? We're going to talk about it in the future in the next slides. And by knowing the estimated color, we are going to use a specific loss function, and by training that loss function, we're going to detect how the network is working, and we will use gradient descent in order to improve it. One important thing about this project is that they were able to achieve better results. They used two methods in order to improve their things. One of them is position encoding, and the other one is a hierarchical volume rendering task, which I'm going to discuss now. So, what exactly is position encoding? The exact objective that the position encoding has is that it's trying to map the input space, which is basically a small space. In our case, we're using X, Y, and Z, and each one is one-dimensional. We want to convert it into a larger space. How does this help us? We're going to talk about it in a bit, but we can basically know that by increasing the dimension of a specific feature, we are going to know much more information and the smaller details of that information. And in this project, they used this formula for the encoding part, which for any value p, we're gonna get a 2L dimension vector output, which every feature of that vector is, for example, over here, we're gonna see the sine, the cosines with the different power of 2 in them. And the way that this is going to help us is converts a 1D data point to a 2LD data point. And in our case, we're going to assume that L for the position data, which represents the X, Y, and Z, are going to be encoded in a 2L space, which L is going to be 10 for the X, Y, and Z, and for the direction data point features, we're gonna upsample it in a space which L is going to be 4. So for every X, Y, and Z, we're gonna have 20 features, and for every direction, we're gonna have 8, which is 2 times 10 and 2 times 4. And how does this affect the result? We can see over here on the right side, we have the result when we don't use the position encoding, and on the left side is when we actually use this method. As you could see, since we use this thing, we are able to show more detailed features of that model. And it's pretty obvious that it's not able to completely show the details of the part of the truck. However, if we use the encoding position, since we know much more about the frequent representative of those data points, we are better able to reconstruct the entire thing. As you could see in this case, if you haven't noticed. Okay, now we're going to talk about the hierarchical volume sampling. What is this exactly supposed to mean? In the next step, we need to sample our data point throughout the 3D space. And how are we going to do it? We're going to use a 3D ray in the 3D space. This 3D ray consists of one origin point called O and a direction vector called D. And as you can see over here, you can see the origin O and the direction D, and we are going to sample specific points on this vector, and with knowing the origin and the direction, we're going to select some data points in the 3D space with a specific X, Y, and Z's, and we are going to use them for our sampling. So here's a better view of the thing that I'm going to discuss about. We assume that the camera is located on origin O, and the direction that it's trying to look is exactly at the direction of the vector D. And throughout the space, there are going to be empty space and also our 3D object. And since we don't exactly know where our object is located, we are going to, at the first step, we're going to equally distribute the sampling point across the ray. And the next step is that this is done in the first section. However, we want to improve our model. What we do is that depending on the values of saturation we got, we are trying to resample the data in a form that we are going to choose the data that are generally more located towards the places where the saturation starts to increase, which sort of shows the edge of the object. And as you could see, since the saturation around the cloud is increasing, we could assume that the edge of that object is located over there. So the model will try to increase the number of data that it's trying to sample in that part. And this image again shows that since we know the edge is close to a specific point, we start to take more samples from that data, from those points. Okay, in the next step, we're going to talk about our network's architecture. The input is going to be gamma x. X is the 3D position vector, which consists of x, y, and z. However, we were using our position encoding, which increased our data points from a low dimensional space to a high dimensional space. And after that, we are going to pass our position encoding data in a 9-layer linear network, and as output, we're going to get 256 features, which we're going to use for next part, and also our density parameter, as you could see in here. However, in the middle of the network, we are still going to pass the encoded position to our network in order to solve the vanishing gradient problems. And as I just mentioned, right now the output is going to be the density parameter and a feature vector of 256, and we will concatenate them with the encoded direction, which we basically still use the same method as mapping the low dimensional data to high dimensional data, and by using the new features and concatenated features and passing it through a bunch of other linear layers, we are going to get the RGB image in the output, which is a 3-dimensional data point. And the reason that you could see over here the dimension of the position encoding is 60 is that we have 3 features, X, Y, and Z, which is 3. And in the previous slides, I showed that LX is going to be 10, which basically is trying to say that we are going to map each data point from the input space to a 20-dimensional output space, which is 3 times 20, which is 60. And that's the reason for 60 over here. And for the gamma D down there, which shows 24, it's basically 3 times 8, which 8 is 2 times 4, the latent space that we were going to use. If you have noticed from the model that we showed in the previous slide, the output density feature is only dependent to the location X, Y, and Z. However, the color is dependent to both the location X, Y, and Z and also the direction that we're trying to look at it. They did an experiment and they realized in this slide as well, you could see that we have two views, view 1 and view 2, and we're looking at the same space, same position, however the color is slightly different. This shows that the direction is going to affect the color in the very end, and it will eventually make the 3D object that we are trying to render much more realistic. And they also done an experiment over the Lego truck, and they assumed that the output color is only dependent to the location in one case, and in another case, they assumed that other than the density, the color is also dependent to the location only, and it doesn't have any dependency over the direction. And the result shows that if you look at the same location, the output is going to be the same. And on the right side, you could see in our image that the tire is completely black. However, if they assume that the direction did matter, the color is going to be slightly different depending on where we're looking at it. Okay, so to summarize a bit of the steps, we had this network that we use the position data combined with the direction data, and after passing it through a network, we're going to get the RGB colors and also the density. So if we want to visualize it, it'll be something like this, as we have this two rays, for example, we have on the left, which each ray could also represent some 3D key points in the space. And we select those data points and we pass them through our network. And what are we going to get? We're going to get, for each individual of these data points in the previous space, we're going to get a density parameter and also a color, which we're going to use for the color voluming. So how did they actually do the volume rendering? They use this formula where alpha I is this function, and in this function sigma I is the density that we got from our previous network, delta is a constant parameter, and ti is going to be the distance between that specific point in the 3D space with relevant to the camera. Other than that, there is going to be parameter ti, which is used in this form, and we just put the all of these numbers in the formula and we will compute it. And we are going to have two different estimations for the color. One is basically from our uniformly distributed data points, and we're going to call it our coarse volume. And the other one is called the fine volume. What are the difference? The coarse volume is going to be extracted from equally distributed data points throughout the array. However, we mentioned that we use a hierarchical way to increase our data points in a case that the number of samples that we got around the edges is going to be high. And by using those new key data points, we are going to detect a new color or a different color called our fine volume. Okay, now let's go to our loss function. The loss function is described as below, where R prime is the set of rays for each batch. CR is a ground truth that we already have from our data set. CSC is going to be our coarse volume predicted, which we estimated a color when we were using the samples from our uniformly distributed samples. And by using them, we were able to predict a specific color, and that's going to be CSC. And we use that hierarchical method in order to increase our number of samples around the edges. And the color that we predicted with those new data and also the previous data that we had, we were able to predict a different color, which we will call CF, which is the fine volume color. And our entire loss function is gonna consist of two parts. One part is gonna be the L2 norm difference between the fine volume and the ground truth, and the other part is going to be the L2 norm difference from the coarse volume predicted and the ground truth. Okay, now to the training part. For their model, they used two different data sets. One of them was the diffuse synthetic 360, which consists of thousands of images, in fact, PNG images. And the other data set was the realistic synthetic 360, which consists of thousands of images, which were JPG. And other than that, they had these hyperparameters for their model, which NST represents the number of data points that they sampled by using a uniformly distributed over the array, and NF is the additional data points that they sampled from the new method that they had, the hierarchical one. Other than that, they trained their network with the Atom optimizer with the default hyperparameters, and they use the weight decay for learning rate, which they use the exponential method for it. Other than that, they trained their model for 1 to 2 days over this device, the GPU V100 Tesla. Now, for the results, they compared their own model with four different models, and the results showed that in most of the cases, well, technically all of the cases except for the case where they compared their model with other models over the chair data set, they basically outperformed all of them, and this shows that their model was pretty good in the 3D representation from 2D images. And here you could also see a visual comparison between their models and the other previous models that we mentioned in the previous page. And here are the references. And thank you very much for your time.